Alright, welcome to another video podcast. In this episode we're going to be taking a look at polar curves and how to integrate inside a polar curve using polar curves, the area formula for polar integration. Let me just quickly remind you of what the formula is and then we'll get started here. If you're integrating something involving polar curves, then the area can be found by taking 1/2 the integral from what I call theta 1 to theta 2. In other words, this is sort of the starting angle of rotation and the finishing angle of rotation to cover the entire region of r squared d theta. Now I want to just emphasize that when I say r squared, I mean r as a function of theta squared d theta. So for this particular example, we're given r of theta. That's easy enough. I mean, I'm looking at the graph. It's a polar curve. It's not a circle. Notice it's flat on the bottom end. So this is actually a class of polar curves. And for this particular example, there's really not a ton of work to be done except for trying to determine what theta 1 to theta 2 are, and then we'll carry out the integration. Well, I think it seems fairly obvious, at least I hope it does, that if you're integrating here from 0 being the starting angle, so if I was to integrate starting at 0, this is theta equal to 0. And as I rotate around, remember we rotate counterclockwise, this would be theta equal to pi halves. This would be theta equal to pi. Down here would be 3 pi halves. And then we would complete the circle, or the figure, by going all the way back to 2 pi. So integrating from 0 to 2 pi is enough to cover the entire region where the radius at each angle is given by 4 plus 2 sine theta. In other words, the angle, as it changes, so does the radius. The radius is really small down here and it's largest up here. And that has to do with the sine function for this particular example. And so if we just directly plug into the formula, we have the integral from starting at 0 to 2 pi of r of theta. Remember, I need the whole thing to be squared, d theta. So let's do a little bit of the integration here together. I'm going to start off by squaring both sides here. And I'll get 16 plus 32 sine theta plus 4 sine squared theta d theta. And on the surface, this is going to be really easy to integrate. I can go ahead and divide through the 2 quickly. The only thing I want to remind you of is your half angle identity here. In other words, recall that sine squared theta is 1 minus cosine 2 theta divided by 2. And so if I apply that particular step at this point, then I'll end up with 8 theta, and then we have the sine theta here. Its integral is minus cosine theta, so it'll be minus 16 cosine theta. And then I've got 2 times this. So if I have 2 times this amount, then clearly the 2's are going to cancel here, and this is going to leave me 1, which integrates out to be theta, minus cosine of 2 theta. Minus cosine of 2 theta becomes minus sine of 2 theta, but then I'd have to divide by 2. So for this particular example, it would be sine of 2 theta divided by 2, and then I'm evaluating the whole thing from 0 to 2 pi. Now, as I look at this particular example, a lot of things are going to cancel out. I notice, for instance, that I have an 8 theta and a theta here. That's really just 9 theta. minus 16 cosine theta minus sine of 2 theta divided by 2. And if I try to plug in the 2 pi, the only place where I'm going to get any contribution from 2 pi is by plugging in to the theta. And when I do that, I get 18 pi from this first part. If I try to plug in the 2 pi into cosine, cosine of 2 pi is 1, so I get a minus 16. And then sine of 4 pi is 0, so I'm done with the 2 pi. Similarly, if I try to plug in 0, I get nothing from the theta. I still get a 1 from cosine of 0. And I get nothing from sine of 0 because it's also 0. This is going to cause the 16s to cancel out, and it's going to leave me an answer of 18 pi for the total area. Now, this is very typical of polar integration problems where you have to resort to those trigonometric integrals we talked about at the beginning of the semester. Using either the half angle for sine squared or cosine squared is usually the best way to go about a lot of these. Just keep in mind that you have to understand sort of how the angle of rotation affects the radius of the figure. Most of the time I'll give you either the figure or the equation, probably both. So the problem will look very similar to this. Alright, thank you for watching.